Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 2 of our unit Mechanical Properties of Fluids. So let's begin with today's session. In today's session we are going to discuss about the Pascal's law. So let's have a look what Pascal's law is all about. He says that it's a pressure applied to any part of the enclosed fluid at rest is transmitted undiminished to every portion of the fluid and to the walls of the vessel. So this is the fluid and this has been filled in one of the container. So this said that this is going to apply a pressure in the every direction. It is looking like this, that it is going to apply this pressure on this every walls of the container, and this pressure is transmitted undiminished to every portion of the fluid and to the walls of the vessel. So let's have a look that if you have if you have uh, let's suppose a certain droplets kind of thing, and if you see its boundaries, that this all drops is applying a pressure from perpendicular to them. So if squeezed liquids comes with equal sweep from all holes, so if you are going to squeeze the liquid from this part, then liquid will come out from all these holes with equal speeds. Now let's prove this, that how this can be justified, that this when they are at rest they will have a same pressure. So what we have suggested is, consider a small element in the interior of a fluid at rest, and the element that we call as an ABC and DF is in the form of a right angle prism. This is the element that we are talking about, and every part of this element is considered at the same depth from the liquid surface, and therefore the effect of gravity is same at all these points. So this is considered as a very small, and if it has been considered as a very small, we can ignore the effect of gravity and rest. Let's find it out. Suppose the fluid pressure that we call PA, PB and PC is acting on the faces, that is the B, E, F, C. It is this face B, E, F and C, and ADFC and ADEB. So PA, PB and PC. This all are the different faces. It's an ADFC face as well as it's a ADBE. So three pressures were applied. It's a PA, PB and PC. The corresponding normal forces are FA, FB and FC as shown in the figure, that this is the force FA, this is the force C and this is the force B. And let's suppose AA, AB and AC as the respective areas of three faces in various directions. So from the Newton's law, the force should balance in various directions, and so that along the horizontal, let's say this is FB cos 90 minus theta 2, that should be is equals to FC, because they are in equilibrium, and we know that cos 90 minus theta, that could be said as a sine theta, so it's a FB sine theta 2, that should be equals to FC. Now in the vertical direction it is FA, and it's an FB sine 90 minus theta 2. This is what FB sine 90 minus theta 2, that would be equals to FA. And from this, if it is sine 90 minus theta, that would be the cos theta. So this will be FB cos theta 2 would be equals to FA. In the same way from the geometry, it could be written as that this area is the AA, this area is the AC and this area is the AB. This angle is theta 1, this angle is theta 2. From the geometry, it's an AC is equals to AB sine theta 2, and from the AA it's an AB cos theta 2. Now let's take the ratios. It's an FB sine theta 2 divided by AB sine theta 2, that should be is equals to FC by AC, as well as FB cos theta 2 divided by AB cos theta 2, that is equals to FA by AA. So This 2 could be gone, this 2 could be gone, so this will represent FB by AB is equals to FC by AC, as well as FB by AB is equals to FA by AA. So from this it is FB by AB is equals to FC by AC is equals to FA by AA. So pressure exerted is same in all directions when fluid is at rest. Thus Pascal's law is verified. I hope this is clear. Is it? Is it clear? Next, let's look at the applications. Let's look at the applications of the Pascal's law. First application, it's an hydraulic lift. So what the situation is that you have two different cross-sectional areas and you have made up a two pistons. This piston is having the cross-sectional area of A1 and this piston is having the cross-sectional area of A2. Let's suppose you are applying a force from this side. If you are applying a force from this side in the downward direction, then this piston will force to this fluid, and this is generally incompressible fluids which cannot be compressed. And if this is not going to be compressed, this is going to move in this direction, and it will apply a force in the upward direction on the second piston. If if this is the case, so what I understand is that pressure applied from this has been 100% transmitted over this. So what I can write, it's a pressure which is equals to F1 by A1 should be equals to F2 by A2. And if I compare this to, then I could have it's an F2 which is equals to F1 multiplied by A2 by A1, or it's F2 which is equals to the weight. If we have applied a certain weight over here, this is equals to F1 multiplied by A2 by A1. Thus the force exerted on the second piston is increased by the factor which is equals to the ratio of A2 by A1. I hope this is clear. This is clear. Is it? Let's look at this. Probably you will have a feel of this. That let's suppose this person is going downward, and as you can see that as he is moving downward, this lift is moving upward. Now a reverse situation has been set up, that again this, look at this situation. Have you seen this? Do you do you understand how the hydraulic lift works? Look at this one more time. Yes, quite interesting. Yes, great. So this is the situation. It's a force by area is equals to constant, and pressure pressure transmitted on both the sides are equal. Then if it's a F1 P1 equals to P2, and from this it's an F1 by A1, that should be is equals to F2 by A2. If A1 is less than A2, if A1 is less than A2, I hope this is clear. Is it clear? Is it? Now let's see this according to the some figure and facts. That means we can have certain more understanding. This was the situation. This was the smaller cross sectional area. This was the larger cross sectional area. Let's call this A1, this is A2, this is going to be downward, and so this is moving in the upward direction. Let's suppose A1, it is of 10 centimeter square, and this A2, it is of 1000 centimeter square. This force here applied, it's an, let's call a 10 into 10, a 10 kg object has been returned, so it's a basically mg kind of thing. So this is equals to 100 newton. I want to find out the force acting on this. So what I can write, it's a pressure at 1 is equals to pressure at 2. This is equals to F1 by A1, that is equals to F2 by A2. So from this it's an F2 which is equals to A2 by A1 multiplied by F1. So this A2, it's a 1000 centimeter square. This A1, it's a 10 centimeter square. multiplied by F1, it's an 100. So this has gone. It's a 100 into 100, which is equals to 10 to the power 4 Newton. So even if you put a small 10 kg object, even if you put a small 10 kg object which is having the weight as an mg, this can apply, or this can pass on an enormous amount of force on the second piston, and this is how this hydraulic lift works. Now I hope you are clear with this concept. Are you? Now do you have any doubts? Do you have any doubts? Is there anything? Is there? No? Great. Let's look at the second application. It's a hydraulic brakes. So what happen in hydraulic brakes is that when we apply a force on this pedal, that this is braking pedal, this will pass on this fluid on this, and this is probably the cross sectional area A1, and this is the different cross sectional area, and it will apply to this. These are the wheels of your vehicle, and when you pedal here, this will pass on this fluid to here, here to here, here to here, and this fluid will be applied on this, and brakes will be applied. So even again the same thing here, two different cross sectional area is going to be used, and when this two different cross sectional area is going to be used, that means you are applying a brake by a very little and a gentle push that can apply a very good amount of force, and that higher amount of force is required, because if you understand the motion of the vehicle, if you take in case of a car, generally in a normal speed we are moving with a speed of 60 kilometer per hour, 70, 80 kilometer per hour, and when I need to apply a sudden brake, then I need a large amount of force to be applied on it. So again in this situation, this F1 by A1 should be is equals to F2 by A2. I hope this is clear. Is it clear? Is it clear? Even one more thing is that the volume of fluid that has been passed through this has been passed through this volume of 2, that could be written as A1 into D1, that is equals to A2 into D2. Please, for the hydraulic brakes, please do remember this too. So if we apply less force over a small area, we can produce a large force over a large area, that we have seen. I hope this is clear. Is it clear? Now let's work for one of the question based on this, that in the in hydraulic brakes, if larger cross sectional piston having having area of 100 centimeter square, and smaller one having area of 10 centimeter square, if we push liquid, I mean fluid, if we push the fluid by 10 centimeter on smaller cross sectional area, what would be the displacement in larger one? Because we have already seen the effect of force on both the sides by F1 by A1 is equals to F2 by A2. Now we want to see this effect, that let's assume it's a V1 equals to V2. This is A1 into D1, that is equals to A2 into D2. When this was the situation, this is the, let's say, large piston, this is the small piston. So if this is the large piston, its area would be 100 centimeter square multiplied by D1, that I want to know, and it is equals to a smaller piston would be having the cross sectional area of 10 centimeter square, and we have pushed the liquid by 10. So this is equals to 100 into d1 equals to 100. So this d1 is equals to 1 centimeter only. I hope this is clear. Is it clear? So now I hope you are clear with the concepts of hydraulic brakes and how and why it has been used. Even we are using a different apparatus. Even we are using the different apparatus at the hydraulic system. Even hydraulic baths are there. If you have visits the hospitals, or I should say a good hospitals, they are having the hydraulic baths, and so that patients feel very comfortable when he just want to sleep on it or he just want to sit on it, because a patient is every time not in a situation to sit by himself or by herself. So hydraulic baths can help. Even now we are keeping the hydraulic beds are there. Yes, they are the hydraulic double beds with storage. We are using this. If you remember the previous situations that beds with storage were there, double beds with storage generally we use in our homes or generally we use in our the flats, that we use it. But before certain time there were no hydraulics were there, and if it was the case that where no hydraulics were there, it was very uncomfortable and it requires a larger amount of force to make it up, to make it down, and to load something into that storage or to remove something from that storage. Now, after the invention and after the use of this hydraulic systems, it is very easy. It is very easy. Just a 5 year or 10-year old kid can operate it. So this all are the applications. Even at the various stages, the hydraulic doors have been used. They are very comfortable. So this all are the hydraulics machines that we use. Now we want to discuss a very important term, that is hydrostatic paradox. What it is, let's have a look. It's the shape of the vessel containing the liquid does not affect the pressure. This is known as the hydrostatic paradox. Let's look at this. This is the one shape, this is other shape, this is third shape. But if you see this, all are having the liquid at this at the same height. That means if you see at the pressures at A, B and C, then at every position, pressure is same, even though they are having a different liquids above it. Yes, as you can see this from the geometry, probably this is the liquid B, this is the liquid A. Amount of liquid over section B is much higher as amount of liquid in the section A, but it does not have any effect. So it is found that all the vessels of different shapes holding different amount of liquid up to the same height, then same pressure is recorded at the base of each of the vessel, and it's the pressure exerted by column of liquid on the base depends on the height of the liquid and not on the shape of the containing vessels. I hope this is clear. Is it clear? Is it? So please keep this in mind, that fluid pressure depends on that. When I say it's a fluid pressure, this depends on the height of the liquid column, that depends on the density of the liquid, and it depends on the G. While I say H, it's a height of liquid column. This, it's a density of fluid, and G, it's an acceleration due to gravity. Yes, and this does not depend on the shape or amount of fluid contained by container. So you cannot think that higher the fluid or the higher the amount of fluid can apply a larger amount of pressure at the bottom. It depends on the height of the liquid column, it depends on the density of fluid, and it depends on the acceleration due to gravity. I hope this is clear. So from this even it must be clear that if this was the situation, that this is one of the fluid and this is another fluid, and they have been filled up to same level. Yes, so this is pressure at A, this is pressure at B, and they must be equal. Yes, because H same fluid, that means density same, G always same. I hope this is clear. Is it clear? Are you sure? So let's discuss certain laws of pressure due to the liquid. So following are some laws of pressure due to liquid. We can say pressure inside a liquid increases with depth. So it is basically the height of the liquid column. So H increases, pressure increases. Pressure changes with the density of the liquid because pressure depends on the density, and it's a pressure at a point inside a liquid is equal in all directions. Yes. So it is something like this. Let's have a look. Let's suppose this is the point. So on this point pressure has been applied from every direction, something like this, and this pressure is equal amount of pressure is being applied from every direction. Next, pressure inside a liquid is same at all points in the same horizontal plane. Yes, this is what we have discussed at very beginning in the last class. This was the situation that pressure at A and pressure at B. So at this both its pressure would be the equal. Pressure due to liquid is not affected. Pressure due to liquid is not affected by the shape or size of the container that we have just discussed. And pressure in a fluid is directly proportional to the acceleration due to gravity that we have discussed up till in the previous slides. So this all are the laws of the pressure due to fluid. Please keep this in mind. This will help us to get the numericals done quickly and correctly. Now let's look at the certain quick questions. It says that the pressure exerted by the column of liquid on the base in a vessel depends upon, this pressure depends on, yes, this is going to depend upon the height of the liquid column. Shape of the vessel, no. Volume of the vessel, no. So this would be the correct answer. Next, according to the Pascal's law, pressure is transmitted same in all liquids. Force transmitted same, no. Acceleration transmitted, no. Temperature transmitted, no. So only pressure is going to be transmitted same undiminishedly in every direction in a liquid. Next, pressure of a liquid increases with, yes, it increases with depth. Width and length, no. Shape of the container, no. So depth would be the correct answer. Next, a gauge pressure that we have discussed in the last class of a liquid column of height h, it given as h rho g. Basically it was a P total is equals to P atmospheric pressure plus h rho g, and from this it's a P total minus of atmospheric pressure, which we call as the gauge pressure, which is equals to h rho g. It is the pressure difference which will give me an h rho g. Next, pressure due to liquid column is directly proportional to pressure due to liquid column depth below the free surface. Yes, it depends on the h, it depends on the density. It's volume of the liquid, no. So it's both A and B. And next, it is the total pressure at depth acting due to a liquid column is, it is something like this. This is the container, and this container is being filled with the fluid, and let's suppose this is the point they were asking for. This is H. So from this is atmospheric pressure P naught, and at this point PA, this could be is equals to P naught plus height of the liquid column multiplied by density of liquid multiplied by G. It's a P naught plus H rho G. Yes, this is the correct answer. I hope this is clear. Was it clear? Was it? Do you have any doubts in this? Is there anything? Is there? No? Great. Let's wind up this session over here. This was all about the Pascal's law and its application, as well as we have summarized all things about the pressure generally when it is in a rest. So this was all about the fluid pressure and Pascal's law and its application. Please go through this session number 1. It's a lecture 1 and lecture 2, and this will help you to get all the questions that is related with the pressure and fluid as at rest. Please go through this. Please do as many questions as possible. Thank you. Have a good day. Take care. Bye bye.